Hey brothers, welcome to This Explainer. Today, I'm going to walk you through the exact step-by-step procedures for installing, wiring, and calibrating a pH transmitter for our RO and CDI pure water systems. As engineers running these ultra-pure water or UPW systems, you already know that this transmitter is literally the heartbeat of our chemical dosing and membrane protection. So we're going to go through this nice and steady, making sure every single detail is crystal clear. Let's dive right in. Quick look at our agenda for today. We'll be covering roll and safety precautions, mechanical and electrical installation, the two-point calibration process, parameter setup and testing, maintenance and troubleshooting, and we will wrap it up with the final handover checklist. All right, starting off with Section 1, roll and safety precautions. Look, I need you to confirm your PPE is fully equipped and the power is locked out. Safety is absolutely non-negotiable out there on the plant floor. You need your hard hat, your clear safety glasses, chemical-resistant rubber gloves, and puncture-resistant shoes. If you're handling those calibration buffers and you happen to get any on your skin or in your eyes, you have to flush the area with clean water for a full 15 minutes. No shortcuts. And it goes without saying, but always execute your lockout/tagout before you even think about touching those electrical terminals. Now, please slow down and be incredibly careful when you unbox the electrode. The manufacturer specifically warns us that the sensor contains a highly fragile combination glass bulb and reference junction. A single hard tap against the housing, or honestly, even just rubbing it too aggressively, will shatter that glass bulb and completely ruin the sensor before you've even started the job. Treat it like delicate crystal, brothers. Moving right along to Section 2, mechanical and electrical installation. You're basically wearing two different hats for this part of the job. On the mechanical side, it is crucial that you pick a representative piping location on your stainless steel line that has absolutely zero dead legs. We are looking for a continuous, highly stable flow. At the same time, on the electrical side, you've got to ensure your cable trays keep those delicate signal wires completely isolated. Keep them far, far away from noisy AC power lines and variable frequency drives. Otherwise, electromagnetic interference is going to be your worst nightmare. Let's break down the mechanical steps. When you're mounting the sensor into that stainless steel inline insertion tee, hand tighten the NPT threads first. Then, and this is super important, only use your small wrench for a maximum of 1/4 additional turn. Any more than that and you risk cracking the body. Once it's locked in securely, make sure you actually open the isolation valve. The water has to submerge the sensor so it can activate the KCl gel inside the reference junction. Okay, write this number down, 30 meters. The pH electrode has an extremely high impedance. Because of that, your shielded coaxial cable length must never, ever exceed 30 meters, or you're going to get severe signal loss. Also, you must only ground the shield drain wire at the transmitter end. Never ground both ends. If you do, you're going to create a ground loop that will severely distort all your readings. As you wire up the terminal block, double-check your specific model. It's either going to be 24 volts DC loop-powered or 230 volts AC. You'll wire your 4 to 20 milliamp analog signal back to the PLC or SCADA system, but pay extra special attention to setting those relay alarms. Triggering that high alarm at 8.5 pH, that is exactly what saves our ridiculously expensive RO membranes from carbonate scaling. And setting the low alarm at 5.5 pH is what protects our stainless steel piping from acid corrosion. It's a big deal. Let's move into Section 3, the two-point calibration process. Understanding the isopotential point is the real secret to mastering this system. Think of it as the theoretical 0 point of a pH electrode. It corresponds exactly to a neutral pH of 7.00, which is where the millivolt output is essentially 0. That's your anchor. And it's exactly why the very first buffer solution you use for your calibration is always going to be that yellow pH 7.00 bottle. Now you must follow this calibration flow to the letter. First, wash the electrode gently with deionized or DI water, then submerge it in your yellow pH 7.00 buffer. Give it 1 to 2 minutes for the signal to stabilize, and hit CAL to set your 0 point. Next, and please don't mess this up, do not skip the DI water wash between the yellow and red buffers. If you skip it, you are going to cross-contaminate your buffers and completely ruin your calibration slope. After washing it again, submerge it in the pH 4.00 buffer, or 10.00 if you're running an alkaline application. Press CAL to set the span, and finally, verify that your slope is greater than 95% and your offset is less than plus or minus 0.05 pH. Take a really close look at this temperature compensation cable. You should always be referencing this data when you calibrate because buffer solutions actually change their real pH value based on the ambient temperature. For example, if your plant environment is running hot, say around 40 degrees Celsius, your blue pH 10 buffer is actually going to read closer to 9.89. If you aren't accounting for this thermal shift, your whole calibration is going to be fundamentally flawed from the start. Next up, Section 4, Parameter Setup and Testing. On the touchscreen interface, make sure Automatic Temperature Compensation, or ATC, is turned on, utilizing the built-in P10100 or P1000 sensor. Set your measurement range properly, which is usually 0 to 14 pH, but I want to give you a great pro tip here. I highly recommend you set the damping factor between 2 and 5 seconds. This is the Goldilocks zone. It perfectly filters out minor water flow fluctuations and electrical noise, but it doesn't blind the system to real, actionable chemical changes. Less than 10 seconds. When you do your verification against a calibrated, portable, handheld meter, what you're really looking for is your T90 response time. The T90 is just the time it takes for the sensor to reflect 90% of a step change in pH. For a healthy, responsive UPW system, that time must be less than 10 seconds. All right, getting into Section 5, Maintenance and Troubleshooting. Keep this troubleshooting cheat sheet handy in your tool bag. If your slope suddenly drops below 90%, you probably have a dry reference junction. If your readings are drifting all over the place, check your ATC temperature sensor. But I want you to pay special attention to a sluggish T90 response time. If it takes forever to read, it usually just means the glass bulb is coated in scale or oil. You don't need to throw it out and buy a new sensor. You just need to gently bathe that glass bulb in a 0.1 molar hydrochloric acid solution to dissolve the scale. Just remember, be gentle and don't scrub it. And finally, Section 6, the final handover checklist. Okay, brothers, before we pack up our tools and call it a day, you must physically verify every single item on this list. Check the fitting for 0 leaks under pressure, confirm your slope is sitting comfortably above 95%, test your high and low relay alarms, and perhaps most importantly, make absolutely sure the pH number you see on that local wall transmitter perfectly matches the SCADA screen back in the main control room. If the wall says 7.00, the SCADA screen cannot say 7.20. They have to match exactly. Remember, the job isn't truly done until the paperwork is done. Proper, meticulous documentation is exactly what separates good technicians from great engineers. So I want to leave you with this final, vital question to think about. Is your logbook fully signed off with all the right data so the next shift knows exactly what you accomplished today? Thank you so much for walking through this explainer with me, brothers. Stay safe out there, and let's keep those UPW systems running pure.